Okay, so let's back up a second and talk about Lenz's law, which gives a little bit more of an intuitive, albeit less quantitative understanding of this induction process. So to be clear, Lenz's law gives nothing that can't be determined from Faraday's law, but oftentimes it's easier to just figure out the direction of an induced current using the simplified understanding of Lenz's law than to go through the whole analysis of a loop or something like we just did using Faraday's law. So it doesn't give you anything quantitative, but sometimes we don't need that. So Lenz's law says, I'll type this out. Lenz's law says that the direction of any magnetic induction effect is such as to oppose the cause of the effect. Now, what the heck, right? Let's talk about it. Okay, so Lenz's law is usually summarized as nature abhors a change in flux. And it's, basically what we're seeing here. So the induced EMF is the negative of a change in flux. So it opposes a change in flux. So qualitatively, it means that whatever current is induced in a circuit because of a change in magnetic flux, it's induced in the direction such that the magnetic field that is induced, that this induced current produces, opposes the change in magnetic flux from this original external source. So I'm going to continue to break it down, so don't worry. So we have, let's say we have a loop and a bar magnet. So we have this situation that I kind of drew above. You have a north end and, presumably, obviously there's also a south end up there, right? So let's say we have a loop here down below, right? So there is a magnetic field coming out of the north end of the magnet and going through this loop, which has nothing special on it. It's a conductor. So it can conduct the flow of charge, can conduct electricity. So it's like a metal. Could be the ring on your finger, it doesn't matter. And that loop has some meaningful area that the magnetic field is going through. And so therefore, we have, at this moment even, as described, we have some magnetic flux happening. And I'm going to say, magnetic flux 1, right? But what we need is a change in magnetic flux. So we're going to make a change in magnetic flux happen. So I'm going to take this whole thing and put it right next to it. Copy. And paste. Oops. That's not what I wanted. Copy and there we go. Paste it there. Okay. That's fine. That's fine. All right. So now, this is going to be in the second scenario, and what we're going to change is the same thing we hinted at before. We're going to bring this bar magnet closer. And if we brought it closer and then stopped and then analyzed that point, it's no different than over here in situation 1, because then there's still magnetic flux, but it's not changing. So it's in the process that you're moving the magnet closer to the loop that everything happens, right? And so in this case, you now, if you're bringing it closer, you are increasing the magnetic flux in the downwards direction, right? There's now, over a time interval, there's more after than before magnetic field going through that area of the loop. And so the magnetic flux at a later time, right, at some time 2 is greater than the magnetic flux at time 1, right? The magnetic field emanating from this magnet, which has tiny spinning charges in it, right? That didn't change. You've just brought, the ring closer to where the field is more concentrated. And so there's more magnetic field represented by a tighter density of magnetic field lines here than down here. There's more magnetic field going through the loop. So thus, because there is a change of magnetic flux, an EMF, and therefore current, is induced in this loop of wire, right? Why is a current induced to? Well, if you've introduced some potential difference, then charges are going to flow, right? And so you've induced an EMF, and so therefore charges flow downhill, quote unquote downhill, the electric hill. And it's according to Faraday's law, or Lenz's law. Lenz's law reminds us that this current will be induced in the direction that most reduces the change in flux that just occurred. So this loop experienced a change in magnetic flux such that it experienced an increase in magnetic flux in the downwards direction. And so an EMF is going to be induced such that the reactionary B field, magnetic field, is back in the upwards direction. So I'm going to say B induced. And where does that B field come from? Well, it comes from the current traveling in the wire, right? So we're kind of working at this kind of like a backward scenario. So this current is induced in that direction around the wire because if you use your right hand rule, and if you're looking at your notes, you know what is coming, because I'm going to attempt to draw something that I'm not very good at drawing. But you use your right hand rule here. So you have 1, 2, 3, 4 fingers for most of us. Hey, that's not too bad. And then a big old thumb. How about goes like this? That's the thumb. All right, fair enough. So you use your right hand rule, putting your thumb in the direction of current, which is this pink color, I induced, right? But we're trying to figure that out based on what direction the B field we know needs to go. So the B field we know needs to be up through the center of the ring to counteract the increasing B field down through the center of the ring, right? Because nature abhors a change in flux. The direction of any magnetic induction effect is such as to oppose the cause of the effect. The cause of the effect is this green magnetic field increasing in the downwards direction, and so we are opposing it. So this induced current here is induced in a direction such as to oppose it. So the magnetic field that current creates, because all moving charge creates magnetic field, according to this right hand rule here. So it's induced in a direction around the ring such that the magnetic field that it produces opposes the original external source of magnetic field change flux. So that means that your fingers curl around in the direction to describe the B field. This is B induced. So we know that it has to be up through the center of the ring, right? So if the charges are traveling around counterclockwise, that makes sense to produce a B field that is up through the center of the ring, which is what we want. So working backwards, that determines that the current around the ring must be in that counterclockwise position. If it were going in the other direction, we'd get, downwards, and that wouldn't be opposing the original increase in flux. It would be adding to it, and that's not how Faraday's law works. That's not what Lenz's law describes. So it's opposing this change. You can kind of think of this whole process as like, any loop of wire or current. It's kind of like a whiny baby, and any change just sets it off. And so any change in magnetic flux, and it resists it. It pushes back against it. And as long as things are the same, doesn't matter if there's, a cajillion units of magnetic flux going through it. If it's steady, it's fine. But if something changes on it, it's going to whine about it and resist that change, right? So, not to get quantitative about it, but you can see that that the magnetic flux is reduced by a certain amount because if it's increasing in the downwards direction, it's reduced by this amount that's going back up through it because of the moving charge. And so you can kind of write the total change in magnetic flux at some point during the process that the magnet is moving down, thus increasing the magnetic flux in the downwards direction. That's reduced by the amount of magnetic flux increasing in the upwards direction because of this induced, because of the induced current around the ring, right? It's all kind of coming together. And you can write that the total change in magnetic flux is from point 1 to point 2 would be the flux, magnetic flux at 2 minus the magnetic flux at 1, which is equal to the magnetic flux at 2, which is due to the magnet only, right? That's the green. Here, I'll do color-coded then. So magnetic flux B2 from the magnet minus the magnetic flux that is caused from the induced EMF. So B2 induced, right? That's this stuff that's counteracting. So it's whatever it is from the magnet minus the contribution that this whiny baby ring is reducing it by. And then you have that minus B1 term still there. But this is what I was trying to get to. So this B2, the magnetic flux in the second scenario here, is reduced by this amount that the ring, the induced EMF in the ring, is cutting it down by. So there are 3 other variations to this, and I really want you to either now or after the lecture or some point go through the exercise of determining, because it's a really useful exercise. So we did the exercise of north end of a magnet moving towards the ring. You can also have the south end of a magnet moving towards the ring. You can also then have the north end of the magnet moving away from the ring, and the south end of a magnet moving away from the ring, right? So the differences would be, for the south end, the magnetic field is going towards the end of the magnet. And for the north, moving away, or just either of them moving away, that means that it would be increasing in one direction or the other, right? So in this case here, we had the B field increasing in the downwards direction. Well, in the other direction, if the north end were moving up, the B field would still be pointing down, but it's decreasing. So there's variations to think about, and you can determine what direction, counterclockwise or clockwise, the current is induced, or the EMF in this loop is induced, such that it produces current in that loop for each of those other 3 scenarios.